Do you remember in 2012 when the world was supposed to end? Turns out, didn't happen. Good thing, because now we have record of the 2012 high school level American mathematics competition. Last time we took on the AMC, the problems were pretty straightforward, so we did 2 in 1 episode. Honestly, I can't believe how easy some of these problems are in what's supposed to be a high school level competition. So we're going to do 3 problems today from the 2012 A exam of the high school level AMC. Now, I know for a lot of you, the first 2 problems are going to be really easy, but if we're going to do the problems, we're going to do the problems. So I'm going to explain them to the best of my ability for any audience. The first problem is about a bug walking back and forth on a number line. The second problem is a basic rates problem about a dynamic duo of cupcake frosters. And the third problem is more what I'd expect from this level of competition. It's a good basic probability problem, which is also going to take a little bit of combinatorics thinking too. Hey, my coffee's ready right on time.
It's time for Coffee with Wrath of Math.
There is nothing I'd rather be doing right now than solving this problem with you. Let's do it. You might be saying, Wrath of Math, why are you giving us your goofy intro? If only you'd do the problem already, we could be done by now. Well, hold your horses, let's get into it and read the problem. A bug crawls along a number line, starting at -2. It crawls to -6, then it turns around and crawls all the way to 5. We want to know how many units does the bug crawl all together. So take note of what this question's asking. We want to know the total number of units traveled by the bug. We don't want to know the total net change in the bug's position. That's not what's being asked. But for kicks, let's calculate that first. What is the net change in the bug's position? He starts at -2 right here. This is, of course, our beautiful number line. It's got all the real numbers going to -infinity and +infinity. Our center of the number line is right there, 0, separating the negative and positive numbers. So our bug starts at -2 right here, and maybe your bug looks something like that, and his final ending spot is 5 right over here. So maybe we draw the bug there as well. So what's the net change in the bug's position? Well, of course, we can just count the units on the number line that we've drawn here. It's a nice visual aid, and we can just count. 1, 2, 3, 4, 5, 6, 7. There's a 7-unit change in the bug's position from his starting place at -2 to his final resting place at 5, where maybe he died because bugs don't live very long anyways. Another way we could calculate this net change without a number line is just the typical way we compute the distance between 2 numbers on a number line, which is to subtract them in any order. So we could do -2 minus 5 or 5 minus -2, but then you take the absolute value because distance is non-negative. Remember, if the stuff inside an absolute value is non-negative, it won't change it. If the stuff inside is negative, then the absolute value makes it positive. So this would be equal to the absolute value of -2 minus 5. -2 minus 5 is -7, so its absolute value is 7. That's kind of a bad 7. Something like that. So that's the net change in the bug's position. But let's go ahead and answer the actual question, which is asking us the total number of units traveled. Now, to do that, we basically just have to calculate the distance between a couple different pairs of numbers on this number line. Our brave traveling bug started at -2, but he didn't go to 5 immediately. His first stop was at -6. So the bug crawls from -2 to -6. Maybe we draw our bug there at -6. So we want to tally up the total amount of distance the bug traveled. So let's calculate how far he traveled on his first little trip here. From -2 to -6, of course, we could just count on the number line. 1, 2, 3, 4. 1, 2, 3, 4. It's a total distance of 4 traveled. So maybe we even draw a little arrow there and say 4 units traveled for that first leg of the bug's trip. Again, we could calculate that distance using the standard method, just -6 minus -2 minus -2, and take the absolute value of that. -6 minus -2 is -6 plus 2, which is -4. The absolute value of -4 is +4. And again, since we take the absolute value, you could do this subtraction in any order. If instead we did -2 minus -6, that would be -2 plus 6, which is +4, which the absolute value wouldn't change. So again, we'd have +4. Okay, so what's the next part of the bug's trip? Well, there's only one part left, right? After it goes to -6, it turns around and crawls to 5. So that's the last part of the trip, whose distance we have to calculate. How many units is that from -6 to 5? Let's do it this way first, and then we'll take a more visual look. We can just calculate it as 5 minus -6 and take the absolute value. And that's going to give us the distance from here to here. 5 minus -6 is 5 plus 6, which is 11. The absolute value of 11 is 11. This means the distance the bug traveled from -6 to its final stopping place of 5 is 11. There's a nice sort of curvy line to represent that. And again, we could just count that up on the number line too, although that isn't very efficient, which is why it's nice to have this standard method of computing the distance. But let's go ahead and count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like it checks out. So in the first part of the trip, the bug travels 4 units. Then in the second half of his trip, he travels 11 units. So how many units does the bug crawl altogether? The answer is 11 plus 4, or 15. There is nothing I'd rather be doing right now than solving this other problem with you. Let's do it. It's a nice, simple rates problem. Cagney can frost a cupcake every 20 seconds, and Lacey can frost a cupcake every 30 seconds. We want to know, with their cupcake frosting powers combined, working together, how many cupcakes can they frost in 5 minutes? Notice we've got 3 rates going on here. We've got Cagney, who can frost a cupcake every 20 seconds. That's a rate per 20 seconds. We've got Lacey, who can frost a cupcake every 30 seconds, and then the problem's asking us for a rate per 5 minutes. How many cupcakes can they frost together every 5 minutes? I think the most simple way to solve this problem, to bring all these rates together, is to convert these cupcake frosting rates per 20 seconds and per 30 seconds to a per minute cupcake frosting rate, and then we can multiply that accordingly to see how many cupcakes will be frosted in a total of 5 minutes. So let's convert these 2 cupcake frosting rates to a per minute cupcake frosting rate. So for every 1 minute that passes, how many cupcakes can Cagney frost? Well, Cagney's frosting a cupcake every 20 seconds, so how many 20-second periods are there in 1 minute? 1 minute is 60 seconds. 60 seconds divided by 20 seconds is 3, just like 6 divided by 2 is 3. So there are 3 20-second periods in 1 minute. So Cagney can frost 3 cupcakes in 1 minute. Not too shabby. Then what about Lacey? Every 1 minute that passes, how many cupcakes will Lacey frost? Lacey can frost 1 cupcake every 30 seconds. How many 30-second periods are there in a minute? Well, 60 seconds divided by 30 seconds is 2. So Lacey will be able to frost 2 cupcakes every minute. So that is our second rate. Not quite as impressive, admittedly, but hey, what are you gonna do? 2 cupcakes per minute. But now remember, Cagney and Lacey, these are not cupcake frosting rivals. They are frosting cupcakes together. So we can actually combine their 2 rates. Together, how many cupcakes will they frost per minute? Well, we've got 3 cupcakes per minute plus 2 cupcakes per minute. I think you'd agree that's a cool 5 cupcakes per minute. Then finally, the question we actually want to answer is how many cupcakes can they frost in 5 minutes? We know that in a single minute, they can frost 5 cupcakes, so in 5 minutes, they can frost 5 times that many cupcakes. That, of course, is 5 times 5, that's 25 cupcakes. And that is our answer. Now, of course, we knew the answer to the problem would be some number of cupcakes since we can read. But even if we couldn't, if we were to just multiply this rate by 5 minutes, what would we get? Well, the minutes unit would cancel out, and then we would just be left with 5 times 5 cupcakes. That's a cool 25 cupcakes. There is nothing I'd rather be doing right now than solving this final problem with you. I really mean it. Let's do it. This is, of course, the most complicated problem of the bunch, but it's not too bad. It's a good probability problem, so I'll read you the problem, and then we'll go ahead and solve it. We've got Alex, Mel, and Chelsea playing a 6-round game. The outcomes of the rounds of this game are independent. That means the probabilities of certain outcomes in a given round do not depend on the outcomes of previous rounds. We know that the probability that Alex wins a given round is 1/2. Mel is twice as likely to win a round as Chelsea, so we don't have exact numbers for them, but we do know that Mel's twice as likely to win a round as Chelsea. We want to know what's the probability that Alex wins 3 rounds, Mel wins 2 rounds, and Chelsea wins 1 round. Couple important things to note here about what the question is actually asking. This is asking about the probability that these things occur in a single 6-round game. It's not asking for 3 different probabilities, the probability that Alex wins 3 rounds, the probability that Mel wins 2, and so on. It's asking for the probability that this occurs in a single 6-round game. Additionally, it's not forcing a particular order on us. It's not asking what's the probability that Alex wins 3 rounds, then Mel wins 2, then Chelsea wins the last round. It's just concerned with the number of rounds won by each player. So that's what we want to find the probability of. If we start to write down our information, we might write that P of A, the probability that Alex wins a round, is 1/2. Now, in order to solve the problem, we of course would like to know the probability that Mel wins a round and the probability that Chelsea wins a round. We don't know that, but we can figure it out. Let's represent the probability that Mel wins a round as P of M, probability of Mel winning a round. We want to know what that is, and we want to know what P of C is, the probability of Chelsea winning a round. Well, we know what they must add to, and that's pretty useful. What must they add to? Well, they've got to add to 1/2, because someone's got to win each round. So there's a 100% chance, a probability of 1, that someone wins each round. Half of that probability, we know, is taken up by Alex, because Alex has a 1/2 probability of winning each round. So the remaining half must be covered by the probability of Mel winning, plus the probability of Chelsea winning. Of course, we'd like to solve this equation for the probability of Mel or the probability of Chelsea. We know how they relate, so we could do some substitution here. Since Mel is twice as likely to win as Chelsea, we of course know that P of M, the probability of Mel winning a round, is equal to 2 times the probability of Chelsea winning a round, 2 times P of C. So we could do some substitution here. Let's plug 2 P of C in for P of M. Then we'll be able to solve this equation for the probability of Chelsea winning a round. This, of course, means that 3 P of C, because we've got 2 P of C plus 1 P of C, so this means that 3 P of C is equal to 1/2. 3 times the probability of Chelsea winning a round is 1/2. Then we just divide both sides of the equation by 3, which gives us that the probability of Chelsea winning a round is 1/6, 1/6. And we can go ahead and write that over here. Now, since we know the probability of Chelsea winning a round is 1/6, we know that the probability of Mel winning a round, which is 2 times the probability of Chelsea winning a round, must be 2 times 1/6, which is 2/6, which is 1/3. Now we're finally ready to answer the question. What's the probability that Alex wins 3 rounds, Mel wins 2 of them, and Chelsea wins 1? Well, we know that in each round, Alex has a 1/2 probability of winning. We need Alex to win 3 rounds, so we want to take that 1/2 probability and raise it to the power of 3. That's 1/2 times 1/2 times 1/2 to account for the 3 times that Alex will win a round. Now, we can just multiply these probabilities together because the outcomes of rounds are independent. So after Alex wins 1 round, the next round, Alex still has a 1/2 chance of winning. Similarly, we need Mel to win 2 of the rounds. The probability of Mel winning a round is 1/3, so we just need to take that 1/3 and raise it to the power of 2. 1/3 chance of winning a round, and then a 1/3 chance of winning another round. Probability of Chelsea winning is 1/6. We need Chelsea to win 1 round, so that's our last factor here, 1/6 to the power of 1, which is just 1/6. That's our last factor for this step. There's still one really important thing we have to account for here. What we have to remember is that this is just the probability of this event, 3 wins for Alex, 2 for Mel, and 1 for Chelsea. This is the probability of that happening in just one way. If we cube 1/2 and then multiply it by 1/3 squared and then multiply that by 1/6, that's the probability that Alex wins the first 3 rounds, and then Mel wins the next 2, and then Chelsea wins the last 1. Of course, there are a bunch of different ways we could shuffle these factors up. It's going to be the same probability every time, but we need to account for the number of ways it could happen. How many ways could Alex win 3 rounds, Mel win 2, and Chelsea win 1? We've got to multiply this by whatever that number of ways is. Now, there's a total of 6 wins that need to be ordered, right? 3 for Alex, 2 for Mel, 1 for Chelsea. That's 6 objects. We know that 6 distinct objects can be ordered in 6 factorial ways. That's 6 times 5 times 4 down to 1. And that's because we've got 6 positions. Once we place a win in one of the positions, there are 5 places remaining for the other wins. Once we place another win in a position, there are 4 places remaining, and so on. 6 times 5 times 4 down to 1 ways that we can order 6 distinct objects. So we might start by multiplying this by 6 factorial. However, the problem that we have to correct now is not all of our 6 wins are distinct. 3 of them are wins for Alex, so 3 of them are identical. 2 of them are wins for Mel, so another 2 of them are identical to each other, and then there's just 1 for Chelsea. So this 6 factorial has a factor of 3 factorial for the 3 factorial ways that we could swap Alex's wins with each other, but they're all identical. So we want to divide out that factor of 3 factorial. Similarly, 6 factorial has a factor of 2 factorial for the different ways we could shuffle Mel's wins around. We don't care about shuffling Mel's wins around. They're identical, so that doesn't mean anything. So we also have to divide out that factor of 2 factorial, and that's our answer. All that remains is to do some simplification. To try to make things a little more clear, I've just written out an example of one way this event could occur. Alex could win the first round, Mel could win the next 2, then Alex, then Chelsea, and then Alex wins the last round. I think you would agree that if we swap these 3 A's around with each other, that doesn't change anything. It's still the exact same sequence of events. So those are the sorts of reorderings that actually don't matter, that we're getting rid of when we divide by 3 factorial and 2 factorial. Note, of course, since Chelsea has only 1 win, we're not double counting any ways that we could reorder Chelsea's wins, because she only has 1 win. You can't really reorder that. All right, let's just go ahead and simplify this, and we will be on the road to victory. 1/2 to the power of 3 is 1/2 times a half times a half. That's 1/8. 1/3 squared is 1/3 times 1/3, which is 1/9. Then, of course, that's getting multiplied by 1/6, and that's getting multiplied by 6 factorial over 3 factorial times 2 factorial. Those are pretty small. Let's just write out the factors, and it will be very easy to simplify that at a glance. 6 factorial is 6 times 5 times 4 down to 1. We don't need to write the factor of 1. And then we have 3 factorial and then 2 factorial. And we've got some simplification going on here. The 2's cancel out. We've got 2 times 3. That cancels out with 6. And this is all we're left with. What's this equal to? Well, 1/8 times 1/9 is 1/72. And then we still have that factor of 1/6. And then over here, we have 5 times 4, which is 20, times 3, which is 60, and there was nothing left in the denominator. What's this equal to? Well, we've got the 1/72. We've got 60/6, which is just 10. So this is equal to 10/72. 2 goes into 10 5 times, and 2 goes into 72 36 times, and this fraction is fully reduced. That is the probability. That's our final answer. The probability that Alex wins 3 rounds, Mel wins 2, and Chelsea wins 1 is 5/36. And that's it.
The end.
Subscribe for more of the swankiest math videos on the internet.